We tend to imagine our Homo erectus ancestors of 1.8 million years ago as apex predators, stone tools in hand, standing atop the East African food web. But in the archives of modern paleontology, human beings were, more often than not, something else entirely. In the eyes of certain ancient giants, we were slow-moving bipedal rations. When a bite force exceeding 16,000 newtons pulverizes a femur in a single instant, this is not a survival contest between evenly matched opponents. This is a one-sided physical slaughter. 1.8 million years ago, the East African Rift Valley, a pregnant female Homo erectus, standing under 1.5 meters tall, bent forward at the edge of a shallow water margin, foraging. She did not know that 60 centimeters below the water's surface, a pair of vertical slit pupils had already locked onto her Achilles tendon. The giant hidden beneath the silt had just completed its final adjustment of interpupillary distance for range finding. From explosive launch to jaw closure, a crocodile strike lasts less than 0.3 seconds. The peak bite force generated between the upper and lower jaws exceeded 16,000 newtons. That is roughly 4 times the bite force of a lion of comparable body mass. It is enough to shatter the femur of a full-grown adult in a single closure. At the moment she was dragged beneath the water, the giant initiated the maneuver unique to crocodilians, the one modern biologists call the death roll. Rotating along the long axis of its body at an angular velocity of roughly 2 revolutions per second, it physically wrenched the seized limb from the torso. What followed was a cascade of catastrophic physiological collapse. Anatomically speaking, at the instant her right lower limb was fully torn free below the knee joint. The femoral artery ruptured completely at its bifurcation in the popliteal fossa. Blood pumped into the lake water at a rate exceeding 1 liter per minute. Collapsing along with her circulation was the placental circulation. The mother's rapid exsanguination cut off fetal oxygen supply within seconds. The fetus inside the uterus would spend approximately 3 minutes convulsing under anoxia before dying. In 2010, a paleontology team from the University of Iowa published a paper in PLOS 1. From the sediments of Olduvai Gorge in Tanzania, they identified a new crocodilian species exceeding 5 meters in body length, coexisting in space and time with early Homo. They gave it a scientific name of blunt, almost accusatory literalness: Crocodylus anthropophagus. Literally, the human-eating crocodile. In those prehistoric shallows, dense with reed beds and papyrus, our magnificent Homo erectus ancestors, whenever they came to drink, whenever they waded out to fish, were the most routine prey items on the menu of these ancient reapers. Isotopic analysis of Crocodylus anthropophagus remains, cross-referenced with cut marks and bite marks found on hominin fossils in the same layers of Olduvai Gorge, revealed a set of data that overturns the conventional narrative of human evolution. In some stratigraphic horizons, hominin remains bearing crocodilian bite marks account for more than 20% of the total hominin fossil assemblage. In other words, at that time and in that place, 1 out of every 5 of our ancestors whose bones ended up preserved in the fossil record ended their lives inside the jaws of a crocodile. Not in the mouth of a leopard. Not in the mouth of a saber-toothed cat. Not in the mouth of a hyena. In the mouth of a crocodile. The animal that had already been perfecting the physics of ambush for more than 200 million years by the time our ancestors first walked upright on 2 legs. The animal whose body plan has remained functionally unchanged since the age of the dinosaurs. Because it had achieved evolutionary perfection long before mammals ever existed. When Homo erectus, that upstart primate barely 3 million years into its 2-legged experiment, stepped into shallow water for a drink, it was walking into a trap that had been set, refined, and optimized across 200 million years of predatory selection. The stone axe in her hand was worthless. Her larger brain was worthless. Her upright posture, her tool use, her incipient linguistic capacity, every single trait we now use to define the greatness of the human lineage, was worthless in that final 0.3 seconds. Because in that 0.3 seconds, she was not a human being. She was 16,000 newtons of protein, sinking below the waterline. 1.8 million years ago, the eastern branch of the East African Rift Valley, the southeastern margin of what is now the Serengeti Plain in northern Tanzania. Olduvai Gorge. The gorge did not exist yet. The gorge would come later. Only in the last few 100,000 years would a seasonal river called the Olduvai begin cutting down through this plateau, gradually exposing the layered sedimentary strata that recorded 2 million years of hominin activity. At this precise moment, 1.8 million years ago, the landscape was an open shallow basin shaped by volcanic activity. At its center lay a shallow alkaline lake roughly 25 kilometers long east to west and 8 kilometers wide north to south. Paleo-Lake Olduvai. The water was salt. Carbonates dissolving out of the surrounding volcanic massifs bled into the lake through groundwater. holding the pH steady between 9 and 10. A strongly alkaline environment that most freshwater fish species cannot tolerate. But at inlet points along the shore and near underground springs, freshwater injections from the basalt aquifer created a mosaic of lower salinity zones. Freshwater wedges. Inside these wedges grew dense stands of reeds, phragmites, papyrus, Cyperus papyrus, and cattail, providing habitat for catfish, tilapia, and a wide range of invertebrates. The shoreline topography followed the classic template of an East African alkaline lake. Directly adjacent to the waterline was a belt of white salt crust, sodium carbonate crystals left behind after the wet season retreat, reflecting a searing glare in the midday sun. Beyond the salt crust was a green ring of halophyte vegetation, salicornia, saltgrass, Sporobolus, alkali rush. Beyond that, the terrain rose gently into an acacia-dominated savanna ecosystem, with grass growing over 1.5 meters tall in the wet season, wilting to a low, gray-yellow mat in the dry. This shoreline supported an ecosystem of staggering density. Large herbivores gathered here in massive seasonal aggregations. An extinct giant antelope, Pelorovis, with a horn span exceeding 2 meters. Multiple zebra species, Cape buffalo, hippopotamus, elephant. Every day, thousands of these herbivores surged toward the shoreline to drink. And their dung, their urine, and their occasional carcasses formed the base nutrient input of the entire lakeshore ecosystem. At the very top of that nutrient pyramid crouched a kill coalition composed of multiple large predators. First, the giant saber-toothed cats. Layer I of Olduvai preserves fossil evidence for at least 3 large saber-toothed predators. Megantherium, at roughly 100 kilograms. Homotherium, at roughly 200 kilograms. And Dinofelis, approaching the body mass of a modern African lion. Several of these species were ambush hunters, specializing in concealment within brush and tall grass, waiting for prey to walk within short-range strike distance. Second, the giant hyenas, Pachycrocuta brevirostris, recovered from the same strata, reached body weights of 110 to 200 kilograms, more than twice the mass of a modern spotted hyena. Its mandible was abnormally robust, and its molars possessed extraordinary bone-crushing capacity, capable of splintering the femur of a juvenile elephant. It hunted in packs and was, in that period, the most formidable scavenger-hunter hybrid on the savanna. Then, the direct ancestor of the modern lion, Panthera leo fossilis, larger in body mass than a modern African male lion, taking down large ungulates through cooperative hunting. And in the water, crouched the most silent, and possibly the most lethal, member of the coalition, Crocodylus anthropophagus. The Brochu team's 2010 paper described the anatomical features of this crocodile in precise detail. The skull length reached over 60 centimeters, from which a total body length of 5 to 6 meters can be inferred. Slightly smaller than the largest Nile crocodiles alive in Africa today. But still, in absolute terms, an apex freshwater predator. Its most distinctive feature was a pair of prominent conical bony protrusions above the eye sockets. 2 small horns. A feature that has never been documented in any other known crocodilian species. The function of these bony protrusions is still debated. Possibly related to sexual recognition. Possibly to underwater camouflage. Mimicking floating debris. Its distribution was concentrated overwhelmingly within the freshwater wedge zones of Paleo-Lake Olduvai. Precisely where the reed beds grew thickest. Precisely where the fish were most abundant. Precisely where early Homo would have been most likely to come to fish and to drink. And somewhere along that shoreline, a small group of Homo erectus was moving slowly. Homo erectus, 1.8 million years ago, stood at a critical inflection point in the evolutionary history of the genus Homo. Their bodies had already diverged conspicuously from the earlier Australopithecines. Adult females averaged 145 to 155 centimeters in height, 40 to 45 kilograms in body mass. Adult males averaged 160 to 170 centimeters, 55 to 65 kilograms. This was a significant size increase over the Australopithecines. And the limb proportions had shifted markedly closer to those of modern humans. Their femora had lengthened. Their tibiae had become relatively slender. Their pelvis had narrowed. Every one of these traits pointed to a single functional convergence. They had fully adapted to long-distance walking. And possibly, to a limited capacity for endurance running. Their brain volume ranged from 600 to 900 milliliters. A substantial jump above the 450 milliliters of the Australopithecines. Though still far below the 1,400 milliliters of modern Homo sapiens. This brain was not yet sufficient to support complex language or fully abstract cognition, but it was sufficient to design and manufacture a stone tool tradition known as the Acheulean. The symmetrical, teardrop-shaped hand axe, bifacially flaked, was the signature of that industry. Their skin had already lost most of its body hair, replaced by a dense distribution of eccrine sweat glands, more than 300 per square centimeter. An efficient thermoregulatory system evolved to cope with the high temperatures of equatorial low-latitude environments. They could walk for hours across the savanna in midday temperatures exceeding 40 degrees Celsius without heatstroke. And this thermal endurance was one of the critical advantages that let them compete with other large mammals. But every one of those advantages failed at the water's edge. The moment a Homo erectus foot stepped into shallow lake water, every terrestrial survival advantage was neutralized or reversed. Bipedal posture had lifted the center of mass above the water's surface. But this meant the lower limbs, below the knee, were submerged, precisely at the height that ambush-hunting crocodiles are optimized to strike. The eccrine sweat cooling system was useless in water. The endurance running capability collapsed to zero when knees were locked in mud. The hand axe was worthless against a target hidden beneath the surface. More critically, the human sensory system possessed a fatal blind spot around the waterline. Human eyes are set on the front of the skull, providing a field of view of roughly 200 degrees. But perception of underwater targets depends critically on the optical state of the water surface. Even light ripples or surface reflections make it nearly impossible for the human eye to penetrate the water column. Crocodilian eyes work exactly the opposite way. Positioned on top of the skull, they can remain exposed above the surface while the rest of the body is fully submerged, showing only two bulging eyes and the tip of the nostrils. Visually almost indistinguishable from a floating log or a clump of drifting vegetation. In this asymmetric perception game, the Homo erectus was the fully exposed subject of observation. The crocodile was the invisible observer. Now push the camera in on the pregnant female bending forward in the shallow water. Her gestational age was likely between 24 and 30 weeks. Her abdomen was visibly distended. And this changed more than the position of her center of mass. It changed her capacity for movement itself. During pregnancy, the ligaments around the human pelvis and sacroiliac joint loosen under the influence of relaxin, preparing the body for delivery. That loosening, while enabling parturition, simultaneously reduces pelvic stability and the capacity for rapid lateral pivoting. Her lumbar lordosis had deepened to balance her forward-shifted center of mass, which meant her spine was more vulnerable to injury under any sudden lateral tension. Her cardiovascular system was operating in the high-load state characteristic of pregnancy. Blood volume was elevated by roughly 40 to 50%. Cardiac output was elevated by roughly 30 to 40%. These changes maintained perfusion to the placenta. But they also meant that under any hemorrhagic event, blood loss would run faster than in a non-pregnant body, and the window before irreversible shock would close sooner. Her act of bending forward into the shallows was a textbook example of what paleoanthropologists call marginal resource expansion. Late in the dry season, savanna prey became scarce and difficult to approach, and lakeshore aquatic resources, fish, mollusks, waterfowl eggs, became a critical protein supplement for Homo erectus. Isotopic analysis of early Homo remains at certain East African sites suggests that aquatic resources may have contributed 10 to 30% of dietary protein intake. For a pregnant female, the value of these aquatic resources was even more specific. Fish are rich in omega-3 polyunsaturated fatty acids, particularly DHA, docosahexaionic acid, a fatty acid that is a critical structural component of neuronal cell membranes in the developing fetal cerebral cortex. A leading hypothesis in paleoanthropology holds that the rapid brain expansion of early Homo was tightly coupled to the systematic exploitation of aquatic DHA sources. Her act of fishing in this shallow water was, in a very literal sense, the collection of raw material for the developing brain of the fetus inside her. A fetus whose adult brain volume would exceed that of every ancestral species that had come before it, and less than 60 centimeters from her knees. Beneath the water's surface, the vertical slit pupils of the crocodile were completing their final range calculation. Crocodilian binocular vision, in the surface plane, produces a stereoscopic overlap of only about 25 degrees. But within that narrow overlap zone, the accuracy of distance estimation is extraordinary. The two bony protrusions above the eye sockets of Crocodylus anthropophagus may have played a role in this calculation, altering the airflow and water flow patterns above the eyes, reducing surface disturbance interference with the visual field. Every micro-adjustment of the pupils, every millimeter-scale rotation of the eyeballs within their sockets, was translated by the optic tectum of the crocodile's brain into a three-dimensional coordinate. Distance to target, 1.4 meters. Depth of target, 58 centimeters below water surface. Angle of attack, 17 degrees above horizontal. Preferred point of contact, the Achilles tendon of the left leg. The crocodile had not moved for the past 46 minutes. Its heart rate had dropped to 2 beats per minute. Its oxygen consumption had fallen to less than 1/20th of its resting rate on land. Every physiological parameter had entered a state that biologists call ambush-ready standby. In this state, a crocodile can hold position indefinitely, waiting for the exact instant when the target moves within the strike envelope. That instant was 1.8 seconds away. The woman shifted her weight. Her left foot pressed into the silt to steady herself. Her right hand reached down toward a rock beneath the water, where she had seen the flash of a small tilapia dart into the shadow. The crocodile's brainstem released the launch signal. The crocodile's attack is a binary switch. Stillness. Then detonation. In Crocodylus anthropophagus. White muscle fiber, the fast-twitch tissue engineered for brief, catastrophic bursts of power, dominates the caudal and dorsal musculature. This composition permits the animal to hold a perfect ambush posture for hours. 4 days. Then, in fractions of a second, to generate propulsive force sufficient to launch more than half of its body clear of the waterline. The tail alone delivers thrust equivalent to 2, sometimes 3 times the animal's body weight. A 5-meter individual. 400 kilograms. At the moment of strike. Nearly 1 ton of forward impulse. The trigger is spatial. Prey crosses a preset attack radius, typically 60 to 90 centimeters beneath the surface. Signal received. The caudal musculature executes a single coordinated S-wave contraction, and the body releases like a drawn bow. The jaws hyperextend mid-strike, the gate between upper and lower mandible exceeding 60 degrees, and slam shut on contact. The closure is powered by the pterygoid muscles, seated at the base of the skull. These are the engine of crocodilian bite force. Evolution has driven their cross-sectional area to a physiological extremum within this clade. In Crocodylus anthropophagus, the osteological scars left by pterygoid attachment sites indicate a peak bite force between 15,000 and 18,000 newtons. Enough to pulverize an adult human tibia in a single closure. The cortical bone of the human tibia fails under transverse compression somewhere between 10,000 and 14,000 newtons. But the bite is only the opening movement. What kills is the roll. Once the jaws lock onto a limb, the crocodile initiates axial rotation, spinning along its longitudinal axis at 1 to 2 revolutions per second. The biomechanical objective is precise. Shear force applied at the point of grip, severing the limb from the torso through torsional avulsion. The magnitude of that shear scales with body mass, angular velocity, and the moment arm of the trapped limb. For a 400-kilogram animal, the forces generated are sufficient to completely detach an adult human lower limb near the knee joint within 2 to 3 seconds. Olduvai Gorge. Bed eye. The sediments preserve the ledger. Specimen OH8. An almost complete juvenile foot. Approximately 1.75 million years old. Early Homo, possibly Homo habilis. Possibly early Homo erectus. On the dorsal surface of the metatarsals. 4 parallel tooth marks. V-shaped in cross-section. Morphology. Depth. Spacing. Brochu's team matched them to the dentition of Crocodylus anthropophagus with clinical precision. Not the conical puncture of a lion. Not the crushing impact of a hyena. The signature is unmistakable, the conical to subconical crown of a crocodilian tooth. Driven into cortical bone. Specimen OH35. The distal tibia and fibula of an adult. The tibial midshaft carries a distinct helical fracture surface, what modern forensic pathology classifies as a torsion fracture. The characteristic failure mode of bone subjected to violent rotational loading. The fracture edges retain the curvilinear texture diagnostic of green bone breakage. Ruling out post-mortem weathering. Tooth marks cluster nearby. The evidence converges on a single reconstruction. The crocodile seizes the lower leg. The death roll generates torsional stress between tibia and fibula. Spiral fracture at the midshaft. The limb is torn free below the knee. This is not an anomaly. This is a pattern. Similar signatures accumulate across other localities in Bed eye. Kubi Fora. On the eastern shore of Lake Turkana. Swartkrans Cave in South Africa. The Awash Valley in Ethiopia. Multiple early hominin sites document predation by crocodiles and other aquatic carnivores on our direct ancestors. Early Homo, expanding its niche toward the lake margins and river edges, paid a staggering price in flesh. So why return to the water? The answer resolves to a brutal energy equation. During the East African dry season, terrestrial plant resources collapse. Large ungulate densities crash or migrate beyond reach. But the lake margin holds. Fish, frogs, waterbird eggs, mollusks. The tubers of aquatic plants. Available. Concentrated. Nutritionally dense. Fish flesh runs to 20% protein by mass. With omega-3 fatty acid concentrations that dwarf anything terrestrial. Mollusks carry extraordinary loads of zinc, iron, vitamin B12, Waterbird eggs approach a near-complete nutritional package. For an Homo erectus population running a caloric deficit, the shoreline meant survival. The shoreline also meant death. Evolution does not weigh motive. It tallies outcomes. Every hominin who carried fish and shellfish back to the group contributed surplus calories and trace elements, raw material for the next generation's neural development. Every hominin dragged beneath the surface was subtracted from the gene pool. Permanently. The negotiation lasted millions of years. It reshaped behavior. Approach the water in groups. Stay in shallows. Read the surface for anomalous ripples. Avoid the reed beds. It may have reshaped anatomy. Certain researchers argue that the elevated thermal sensitivity of human lower limb skin is a residue of this selective pressure. And it shaped something deeper. A phylogenetically embedded fear of water. When a modern human stands alone at night on a dark shoreline, staring at the invisible volume beneath the surface, the piloerection along the back of the neck may be the oldest inheritance he possesses. A gift. 1.8 million years old. From the Homo erectus ancestors who survived the Olduvai shoreline. Olduvai Gorge. Bed-Eye. The sediments here are a geological archive, bound in chronological order. At the base, volcaniclastics dated to approximately 1.9 million years. Above that, lacustrine deposits, fine gray-white mudstone saturated with diatom frustules and carbonate crystals. Interbedded through the sequence, coarser layers of fluvially transported sand and gravel, recording brief wet season floods that swept basalt fragments from the highlands into the lake margin. Within these sediments, the skeletal remains of Crocodylus anthropophagus and early Homo lie in a spatial association that is difficult to look at without discomfort. Same horizons. Same localities. Sometimes separated by less than a few meters. They shared the same paleo shoreline. The same ecosystem. The same nightly transaction. The pregnant Homo erectus female, if she existed in that specific moment, her skeleton will almost certainly never be found. The death roll would have partitioned her body into fragments of unequal mass. The head and torso, likely dragged into deep water, would have been consumed within weeks by aquatic microbes and scavenging fish. The lower limbs, including that torsion-fractured tibia and fibula, likely swallowed whole. Dissolved in the strong acids of the crocodile's gastric environment. Reduced to trace calcium and phosphorus. Voided in feces. Settled into lake-bottom sediment. The fetus leaves nothing. At 24 to 30 weeks, the skeleton is incompletely ossified. Even under ideal taphonomic conditions, preservation beyond a few thousand years is nearly impossible. During the 3 minutes his mother spent submerged, he passed through hypoxia, cardiac arrest, brainstem failure, a life that never opened its eyes, extinguished before its first independent breath. But she is not entirely without trace. The bed-eye fossils bearing crocodilian tooth marks, OH8, O35, and the specimens recovered since, are the collective testimony of countless women like her. The preservation odds are vanishingly small. Only a fraction of remains are abandoned in the shallows. Only a fraction of those are rapidly buried. Only a fraction survive the subsequent millennia of decomposition and weathering to reach a microscope stage 1.8 million years later. Behind every such fossil may lie thousands of attacks whose evidence dissolved into time. When Brochu's team named the species, they must have hesitated over the epithet. Anthropophagus. A Greek compound. Anthropos, human. Phagian, to eat. Within the conventions of biological nomenclature, deploying a word that emotionally freighted as a species name is exceptionally rare. Most species are named for their discoverer, their locality, or a neutral morphological trait. Brochu chose this name because the evidence refused neutral language. On the shores of an East African lake, 1.8 million years ago, a species of crocodile treated human ancestors as a stable and significant component of its diet. Not opportunistic. Not accidental. A systemic predator-prey relationship, deeply integrated into the shoreline ecosystem. In that ecosystem, our ancestors were not purely predators. Not purely scavengers. They were also, in certain places, at certain hours, a protein source. This inverts a quiet assumption embedded in the classical paleoanthropological narrative, that our lineage was, throughout its evolution, the master of its environment. The truth is more complex. And more brutal. Across the long transition from Australopithecus to Homo erectus to Homo sapiens, our ancestors spent substantial stretches of deep time as the hunted, the pursued, the consumed. Every tooth mark on their fossilized bones is physical evidence of that predation history. And at the end of that history, something shifts. Approximately 1 million years ago, early Homo begins systematic control of fire. The hearth. At night. Dieter's nocturnal predators. Around 500,000 years ago. Projectile weapons. Thrown spears. Later. The bow. Threats now engaged at distance. Around 40,000 years ago, Homo sapiens begins constructing durable shelters, migrating sleep from open exposure into enclosed space. Every technological increment is a late repayment. A debt owed to the ancestors dragged beneath the water at Olduvai 1.8 million years ago. They paid in flesh so that later generations could inch closer to control over their place in the ecosystem. Their bones were left in the mud of an ancient shoreline. Buried, compressed, dewatered, mineralized. 1.8 million years later, a team of paleontologists in khaki field clothes lifted those bones out of the mudstone, one fragment at a time. With small trowels and toothbrushes. The bones were numbered, photographed, scanned, written into journals. 08, 035, 062. Behind every catalog number, an individual who once possessed a heartbeat, a body temperature, hunger, fear. Some of them, perhaps, were pregnant. Some of them, perhaps, were bending in shallow water, gathering DHA-rich fish flesh for the child in the womb. They left no names. They left no faces. They left bones. And on those bones, the tooth marks of a crocodile, an unsigned death certificate, engraved permanently into the mineralized cortex. Nature holds no funeral for them. But the tooth marks themselves are the most honest epitaph, a record of how many generations, on how many unnamed shorelines, a species had to be devoured in order to become us.